Welcome back, everybody. We're going to be taking a look today at what are called Sturm-Liouville problems, or SLPs. This is the topic that is going to lead into all the material for homework set 9. So this has nothing to do with homework set 8, which is due this weekend. It is solely homework set 9 for next week. So we're going to start looking at that material today. This material is pretty well covered in the textbook in Chapter 4. We're going to get through probably 3 sections today, 4.1, 4.2, and 4.3. I do encourage you to heavily read those sections as we're working through the material. Just a quick look at kind of where we are for this week. I have posted the grades for Exam 2. Our lecture on Monday was not videotaped. But I do have all the lecture notes up for that, including the Maple files for you to take a look at. I've already posted these lecture notes that I'm videoing over right now, but the video will go up here pretty soon. This is around 3 o'clock on Wednesday. And that's going to cover sections 4.1 and 4.2, a little bit out of 4.3. And then we'll look at something called the Legendre's equation and some special orthogonal expansions on Friday. Excuse me. And that'll include material from 4.5 as well. So you do have 2 homework sets due that are left in the semester. We've got homework set 8 that's due this weekend, and then homework set 9 that's due next Thursday, and that is before Friday's exam. Remember, we have an exam on Friday. I'll post the answer key for homework set 9 at midnight that night so that y'all can look over it and prepare to take your exam sometime during the day on Friday. But we do have those 2 homework sets. We do have a quiz due this Friday. All the material for that's up, and I believe the quiz itself is up at this point. And that you should watch the videos and review the notes over on this section. So let's just jump right into it. The first thing I want to get out of the way is what the definition of an SLP is. So an SLP is called a Sturm-Liouville problem. It's named for French and German mathematician that came up with this. And before I get too much into the definition, I'll come back to this here in just a second. I want to talk about why this topic is coming up at this point in the course. If you think about our journey in the course so far, where we've done, ever since we started on the material for Exam 2, we've been trying to do separation of variables to solve all these different partial differential equations. And that journey has resulted us in having the same eigenvalue problem almost every time. So we've had y double prime plus lambda y equal to 0 on most of the PDEs that we've solved via separation of variables. Up to now. So that's been our reality, is we keep looking at the same eigenvalue problem over and over and over again. And we've sort of exhausted as far as that eigenvalue problem is going to take us in this course. If we want to be able to solve more complex PDEs, like we're going to try to do the last week of the course, then we need the ability to look at different eigenvalue problems. And those different eigenvalue problems need a general theory to sort of encapsulate them. And the general theory of what an eigenvalue problem would look like for a separable PDE is an SLP. So the definition that we're talking about here today is the most general form that an eigenvalue problem can take in this course and still allow for separability in terms of solving the PDE. So I just want you to understand this is simply a generalization of what we've talked about so far in the course to allow us to solve more complex problems. So the SLP, or Sturm-Liouville problem, is given to us by this eigenvalue problem. You will frequently see me call this operator SY. And so oftentimes when I'm talking about a Sturm-Liouville problem, it's SY plus lambda y equal to 0. So this is the S here that's defined as 1 over Wx, P of x, derivative with respect to x, derivative with respect to x of all of that, plus q of x. This operator, which acts on y, this is called the SLP operator, or Sturm-Liouville operator. But honestly, I just want you to think of it this way. It's basically another way of thinking about what kinds of eigenvalue problems fit a certain pattern. And if they fit this pattern, then we're allowed to separate variables without any problems. So long as there's two different types. There's regular types and there's singular types. And we're able to go through this very easily if the problems are regular. But if they're singular, you'll see as we go through this, there's a little bit more work that has to be done. So you got sy plus lambda y equal to 0 as your basic eigenvalue problem here. Notice our normal eigenvalue problem, y double prime plus lambda y equal to 0, comes from this. You get this if w of x and p of x are both 1 and q of x is 0. So in some ways, the eigenvalue problem that we've been looking at is the simplest possible version of this Sturm-Liouville problem. And we've been looking at what are called symmetric boundary conditions the entire course. So these are what are known as symmetric boundary conditions. And we'll talk a little bit more about the role they play here in just a little bit. But this is the kinds of eigenvalue problems we've been having. This is just the general form of those. If the function w, p, q, p prime, so you need the derivative of p to be continuous as well. If all of those functions are continuous and p and w are positive, so these two terms are positive on the interval, and as long as these things don't have a determinant of 0, that's what this means. You're just making sure that you can solve the resulting system. If all three of those things are true, then this SLP is called a regular SLP. Almost all of the problems that we've looked at this semester have been regular. We are going to start looking at some singular problems. So what makes an SLP singular is if either p or w vanish at the endpoints. So whatever the endpoints of the interval you're studying the PDE on, if p or w vanish at the endpoints, if they vanish inside the interval, then they're not continuous, right? So which means they're not going to be regular. But if all of these things hold and p vanishes at the endpoint, or w vanishes at the endpoint, or they become infinite at an endpoint, or you're on an infinite interval, then the problem is called singular. So you're regular up until the point one of these things goes wrong, and you become singular as soon as any one of these things happens. So in other words, you need all of these for regularity. So all are required. And for singularity, only one of these things is required to occur. Now, all of them could occur on a given problem, but only one of them is required to occur for the SLP to be called singular. So let's just look at an example where we're asked to classify some SLPs to get us used to this new notation. We're going to start with generalizing. So this is a general eigenvalue problem. And I would really like to figure out what the functions p, q, and w are. So that's exactly what we're going to do here. We're going to try to write this in the SLP. We're going to convert this to SLP form. That way I can just give you eigenvalue problems that look like this, and you automatically know how to convert them to this new form that we're talking about today so that you have access to all the theory that we're going to uncover here over the next two lectures. So I'm just going to start with, we define Ly to be the linear operator a2 of x, y double prime, plus a1x, y prime, plus a naught x, y. So that's the linear differential equations that we've been looking at. Sy is our typical, is the SLP that we just defined. It's 1 over w of x, p of x, y prime, prime, plus q of x, y. And it's definitely worth remembering this form. I want to set these equal. So we're going to set Ly equal to Sy in order to determine the function p of x, q of x, and w of x. So if I set these two equal, I've got 1 over w of x, p of x, y prime prime, plus q of x, y, equals a2. And I'm going to stop writing a2 of x. When we see this, we know that these are the coefficients here are allowed to be functions of the independent variable. And so just if we're solving this, you know, if I write this side out, you know, probably I guess the easiest way to do this is just to go ahead and do that. This is 1 over wx. This is p prime, y prime. This is product rule, right? Because you're differentiating a product. So you don't distribute, probably is a little bit misleading. We don't distribute the derivative, we do product rule. So this would be p prime y prime plus p of x y double prime plus q of x y equals this. And if you look at both sides and compare coefficients, for instance, the coefficient of y double prime here is p of x divided by w of x. That has to equal a2. So a2 is p of x divided by w of x. Similarly, a1 is p prime of x divided by w of x. And a0 is q of x divided by w of x. It looks like w of x is playing a huge role here, and in fact it does. I'm more interested in the following, though. P of x will then be a2 times w. P prime will be a1 times w. And q will be a0 times w. So all of this leads me to believe that if I can find w, then I'm well on my way to writing down the SLP form, because as soon as you find w, you can automatically construct p and q knowing the coefficients of a2, a1, and a0. And that's our goal here, is to figure out how that works. So I'm actually going to do the following. We've got p and p prime right here, so I'm actually going to differentiate this one and set it equal to this one. So if I differentiate the top here, this is p prime of x is, once again, remember a2 is a function of x, so this is product rule. So this will be a2 prime w plus a2 w prime. And comparing it here, where you've got p prime of x is a1 w, the conclusion from all of that is that a1 w of x equals a2 w prime, or a2 prime w plus a2 w prime. So if you solve this for w of x, or excuse me, w prime, what you'll obtain is a2 prime minus a1 divided by a2, all of that times w of x. And I think you can see where this is going. This is a differential equation in terms of w, which can easily be solved. We've seen this solution many times. So this has the solution e to the integral of whatever this result is. So w of x, let me just rewrite it here. W of x is given by this, so the assumption is on a problem like this you will know, because you'll be given the general form of the eigenvalue problem, right? You'll be given the eigenvalue problem that looks like this. So you will know a2, a1, a0. You'll be able to use a2 and a1, notice a0's not a part of this, to find this function. And this is a very important function, not only for these problems, but for applied mathematics problems in general. This is something that's called the weight function. And we're going to see why it's called that here in a little bit. So once we have our weight function, then it becomes really easy. You can use W of x to easily determine P of x, Q of x, P prime of x, and transform Ly to Sy. So the idea is you can take a general eigenvalue problem and transform it to this special SLP form, and then we're going to talk about the advantages of the SLP form coming up. All right, so here we have a general eigenvalue problem, just to make it clear kind of the relationship here. Ly on this problem is 2y double prime plus xy prime plus x squared y. And so this problem originally is in the form Ly plus lambda y equals 0. So that's our eigenvalue problem. And we have a Neumann-Dirichlet condition. We could probably, we don't know how to solve these kinds of equations, so it's not an Euler equation or anything like that. It turns out it is an equation that we will talk about here in a couple of days, but I just want to transform this for today into an SLP form and verify if it's regular or singular, and then determine what the weight function is. So we're going to start with the listing of the important variables here. A2 is 2. A1 is x, not 1. It's the coefficient. The coefficients can be functions of x. So A1 is x, and A0 is x squared. Notice I don't need to divide by anything or get a coefficient of 0. It's literally just the coefficients. So these three things will imply then that the weight function is e to the integral of, well, remember our form that we have over here. And I think I reversed this actually. Let me double check right quick. So we've got a2 prime w of x plus a2. So if we're solving for w prime here, yeah, it's the a2 that's going to be negative. My apologies. I'm glad I caught that. It's actually a1 minus a2 prime. I switched them. I knew that looked funny. So a1 minus a2 prime. There you go. So there's your weight function, a1 minus a2 prime over a2. All right, so if we take a look at it down here, we're going to put a1 minus a2 prime over a2 dx. This is how we're going to find our weight function. So this is equal to e to the integral. So if you look here, you've got x minus the derivative of 2 is 0, so x over 2. And the antiderivative of x over 2 is x squared over 4. So that is my weight function. So it's either going to be this one or this one. So we need to decide, is this SLP regular or is it singular? So let's construct the other functions real quick. P of x, if you go back up to our formulas here, P of x is a2w. So a2 times w. P prime is a1 times w. And q is a0 times w. So if we think back to the definition of regular versus singular, we need all of these to be continuous, which they are. So all of these are continuous functions on the interval from 0 to 1, so we're good there. We need w of x and p of x to be greater than 0. We need these to be positive, which they are. So that checks out, that checks out. And then we need our boundary conditions to be symmetric and solvable, and these are standard boundary conditions for us, so they check out as well. So this is a regular SLP as long as something doesn't go wrong with the singularity conditions. So the singularity conditions ask us, okay, are any of these 0 at endpoints, right? And it's not any of them. It's specifically, and you got to be really careful with this, it's just P of x and W of x. So if you look, is P of x 0 at an endpoint? No. Is W of x 0 at an endpoint? No. P prime and Q are, but those don't have to be non-zero at the endpoints. P and W do. So P and W are not equal to 0 at endpoints. That's good. They're also not equal to infinity at the endpoints, and our interval is not infinite. So all of these conditions imply that this thing is regular. So the answer choice is B. Okay, let's do a similar problem here. So A2 is x squared, A1 is 3x, A0 is e to the x. And so let's see, W of x then is e to the integral A1 minus A2 prime over A2. So this is 3x minus 2x, which is just x. So you get x over x squared, or 1 over x. Integral of 1 over x is natural log. E to the natural log is just x. So our weight function here is just x. And you can instantly tell we're going to have some issues with that. But let's go ahead and write. Oh, I probably should have written the form over here. Let me back up to this first problem and write the SLP form. So the SLP form for this problem is 1 over W of x, P of x, times y prime, y prime prime, plus Q of x times y. That's our SLP. Now that's our S operator, right? So the S operator is that. Our SLP then is sy plus lambda y equal to 0. So that's sy. So this is the S operator version. And so this is sy plus lambda y is the form of the eigenvalue problem, which is called the SLP. It doesn't look pretty. I mean, it's not supposed to look pretty. It's a very weird form. And if you were to multiply through and work out all of these things, you would get it in this much nicer form here. But this nicer form doesn't allow us to check things like regularity or singularity, and it doesn't allow us to know what W is. And it turns out for what we're about to do, W is very important. So getting it into these SLP forms is sort of a mandatory thing. I can't just not do that because it looks uglier than the equation we were given. It's important that we know this form. So here, W of x turns out to be x. So I can figure out P of x. P of x is A2 times W, which would be x squared times x, or x cubed. P prime, this is always a good thing to check to make sure that you did this right. P prime is A1 times W, which is 3x times x, which is 3x squared. So you expect to see the derivative of x cubed, which is 3x squared right there. If you didn't, then you did something wrong. And then Q of x is A0 times W, which is e to the x times x as such. So we should check, are all of these continuous? Yeah, absolutely. They're all continuous on the interval. We've got the right kind of boundary conditions. P of x and Q of x are positive on the interval, which is true because it doesn't include the endpoints. So all of the conditions for regularity are satisfied. However, when you get to singularity and start looking, the very first thing we run into is at the endpoint 0. P of 0 is 0 and Q of 0 is 0. Actually, Q doesn't matter, but W at 0 is 0. So these vanish at the endpoints, and that's an automatic trigger to know that this thing is singular. So we know it's singular. There's its weight function, so the correct answer is C. Okay, so we have access to a really powerful theorem And what I'm going to do is state the theorem with you now, and we're going to prove parts of it, but parts of it are sort of outside the scope of this class. What I'm really interested in is the proof of the fact that if you have a regular SLP, okay, then you will always have real eigenvalues. You don't even need to check the complex case. You'll always have real eigenvalues. The eigenvalues are increasing, and you have infinitely many of them. Now, I'm not going to verify this, but we've seen this time and time again. We're also going to prove that any eigenfunctions you get from a regular SLP will always form an orthogonal family on the interval, but it's not orthogonality in the sense that you're used to. It's orthogonality with respect to a weight. So this is a new inner product definition for us. This is the inner product, the L2 inner product with weight W. So this is L2 on the interval from A to B. W is the way that you would say it. So yn are functions of this. Let me write that a little bit clearer. So this is the weighted L2 space on the interval from A to B. So yn, the eigenfunction, is assumed to be a member of that, as are any functions you would put in your initial conditions. What orthogonality means on a weighted space is that the inner product with respect to the weight is 0. And all you do is our normal L2 inner product. So if this were unweighted, W would just be 1, and you would have the integral from A to B of yn times ym. But with respect to a weight, you multiply by whatever the weight function is, and that's how you achieve orthogonality. So the orthogonality condition here means that if these are different eigenfunctions, then they are mutually orthogonal. And that's a guarantee of working with the regular SLP. So this is the importance of this to what is going to come from here on out. We're going to get eigenvalue problems that we have to solve for PDEs, and they're not going to be Fourier series eigenvalue problems, right? They don't lead to a Fourier sine or cosine or any kind of series like that we've seen. So we don't know a priori that the eigenfunctions that we calculate form an orthogonal basis. This theorem says that they in fact do and can be used to form a basis for the solution space. And that's what part B says. This one is outside the scope of the course. So these two, the proof of these are outside the scope of this course. You'd have to prove them in a higher level course because they require some real machinery. But they say that the YNs are complete in that you can have an expansion of any function. Once again, this function lives on the L2WAB space, has an eigenfunction expansion in terms of these eigenfunctions where the coefficient is just like the coefficient you know, but it's the weighted inner product. And then finally, you have the function here. This is what it means for f of x to belong to this space, is that it's a function from AB into the real numbers such that this integral converges. So you can have some gnarly looking functions here, but if your weight function cancels out the bad part of f of x, you can actually get the integral to converge. So this is actually a little bit more general and relaxing the functions that we can work with when we do separation of variables. And then this is what we call the E sub n. This is the L2 error. So we know, or we're guaranteed if you have a regular SLP, that this orthogonal expansion will converge in the L2 sense, and this is what we mean by that, is that the L2 error will go to 0 as the number of terms increases. So this theorem justifies all the things we've been doing all semester with separation of variables, and I'm actually going to prove bullet point 2 and bullet point 4 coming up in just a second. But I feel like before we jump in and prove the result of this theorem, we should look at an example to show that these things are happening in that example, and just to give you a little sense of what it is I'm talking about with a weighted. We haven't talked about orthogonality with respect to a weight. So I kind of want you to see an example to make sure that you feel good about what that means before we head into the theorem. So here's our eigenvalue problem. It's a simple enough problem. But it's not our normal y double prime plus lambda y equal to 0, so we're kind of flying blind here in terms of knowing exactly what's going to happen if I try to use the eigenfunctions from this thing to do any sort of orthogonal expansion. Because up till now, all I've asked you to do is find eigenfunctions for eigenvalue problems like this. I haven't actually asked you to use them to expand solutions for a PDE where this was the eigenvalue problem. So we're learning how to do that in this example. We've got Dirichlet boundary conditions here. We're going to look at the SLP form first. So we're going to try to see if this problem is regular or singular and then go from there. So just looking at it, A2 is 1, A1 is 1, A0 is actually 0 here. So you need to be very careful about that. There is no, the lambda y term is not part of the linear operator. The linear operator is the part that doesn't include the lambda y term. So this is, this is of the form Ly plus lambda y equal to 0. So Ly here is simply y double prime plus y prime. There is no y term that's a part of Ly, so A naught is 0. Our weight function is e to the integral. This will be A1 minus A2 prime over A2, which looks like it's just 1. Which means that our weight function is e to the x. This means then that p of x is, let's see here, p of x would be a2, so it's e to the x as well. P prime of x is also e to the x, which we expect, right? The derivative of e to the x is e to the x. And q of x is going to be 0. So if we write this thing in SLP form, this differential equation can be written as 1 over e to the x. This will be p of x times y prime, quantity prime, plus q of x, which is 0, y, plus lambda y equal to 0. So this is an alternative way of writing this eigenvalue problem here. So this is our SLP form of this differential equation, this eigenvalue problem. And we need to check we're on the interval from 0 to 1. So we need to check all of the things, but you immediately notice that, this is e to the x, e to the x, e to the x is continuous. These are all continuous. E to the x doesn't vanish anywhere, much less at 0 or 1. There's nothing infinite about this problem. We're not on an infinite interval. None of these have an infinite asymptote. So you know that this thing's going to be regular. So the results of that previous theorem apply in this case. So if you were looking to solve this problem, the next step would be, okay, I'm not actually going to solve the problem by using the SLP form, right? And this is what I do need to know, the weight function, right? So the weight function, I'm going to hold on to that for now because that's really going to come in handy, which is why we had to do this in the first place. We also needed to check that the SLP was regular so we know the results of the theorem can help us in what's to come. But in terms of just solving for the eigenvalues and eigenfunctions, well, we're going to do that the old-fashioned way. You're just going to use the characteristic equation, which turns out to be this, which you're going to use, quadratic formula to factor it. And so there are your characteristic roots. You know that the key thing here is whatever makes this 0, which turns out to be lambda equal to 1/4. So we're going to have 3 cases, right? Your first case is going to be, okay, what if lambda is 1/4? Well, if lambda is 1/4, then r is negative 1/2, which is a repeated root, which means our solution is going to be a e to the minus 1/2 x plus b times x e to the minus 1/2 x. And remember the initial conditions, or the boundary conditions here, y of 0 equals 0, yeah. Y of 0 equal to 0, y of 1 equal to 0. And if you apply those, so y of 0 would be a plus 0 is 0, so that tells you a is 0. And y of 1 would be b e to the minus 1/2, which also equals 0, which implies that b is 0. So this case gives you no eigenvalues. So you don't end up with any eigenvalues or eigenfunctions for that case. Case 2 is the case where lambda is less than 1/4. So you've got lambda less than 1/4. So these are going to be, if lambda is less than 1/4, like say lambda is 1/5, you can see here that you get positive roots. You get positive under there. So these are real distinct roots, which means that your solution is going to be a e to whatever the root is. I don't need to write it out here. B e to whatever the second root is. But you know that R1 and R2, this is the case where R1 and R2 are real distinct roots. And so you can test real quick on this. Y of 0 is a plus b, which is 0. Y at 1 is a e to the R1 plus b e to the R2. Yeah, that's right. Which would also be 0 here. So this is this condition tells you that a equals negative b. So you can use that right here to say, okay, well, if a is equal to negative b, then this thing is b e to the R2 minus e to the R1, which has to equal 0. So that implies that b is 0, which you can come back up here and say, well, that implies that a is 0. So you know you're in a situation where both of those 0 out. So in this case as well, you have no eigenvalues. All right, that brings us to our interesting case. And so the interesting case here, which I'll call case 3, is what if lambda is greater than 1/4? Well, if lambda is greater than 1/4, then you know that your root is minus 1/2 plus or minus I square root 4 lambda minus 1 over 2, because we're assuming that the value inside here, we want that value to be positive because we're trying to find the frequency. So we're automatically getting complex characteristic roots. And I want to make sure you understand we're not violating the theorem. If you go back and look at what the theorem says, we will always get real eigenvalues, not that we'll always get real characteristic roots. Right? So these roots here, these characteristic roots can be complex. In fact, most of the time they will be if we're going to end up with eigenvalues. And so we know that the solution in this case is an oscillation. It's an oscillation of this form, e to the minus 1/2 x, c1 cosine, square root 4 lambda minus 1 over 2, c2 sine, square root 4 lambda minus 1 over 2. So we're familiar with this. We know that this is the form that the solution will take. If we look at the boundary conditions, y of 0 would turn out to be, I believe, just c1 is all that survives there. Sine of 0 is 0. You get cosine of 0 is 1, and that's 1 as well. So we know that c1 is 0. So if you look at y at 1, it's e to the minus 1/2 times 1. c1 is 0, so forget the cosine term. You would get c2 sine of this, and this is supposed to be 0, but that automatically implies that this thing is a multiple of pi, where n can be, well, n can't be 0, because we know we don't have that would be lambda equal to 1/4, and we know that's not a part of it. So this is plus or minus 1, plus or minus 2, and so on. And if you solve for lambda, you find that lambda n here is n squared pi squared plus 1/4. And so these are your eigenvalues. Now, we've done problems like this previously in the course, but this is as far as we've been able to go with those problems. Yn in this problem, the eigenfunctions would be, you see that they're sine. You've got the constant here. So looking back at this, the C1 term is gone, so your eigenfunctions are a constant times e to the minus 1/2 x sine. So yeah, I'll just go ahead and write it all in. Well, just so you can see, if you plug this in for lambda right here, what you'll see happen is it's equal to n pi, that thing that's right here, right? So square root of 4 lambda minus 1 over 2, that term is equal to n times pi. So this ends up being n pi x for the eigenfunctions. So up till now, we've been able to get this far, right? We've been able to say, here are my eigenvalues and eigenfunctions, but we haven't been able to go any further than that. This theorem allows us to use these safe in the knowledge that these new eigenfunctions form an orthogonal set with respect to the weight function w of x that we obtained earlier when we put it in SLP form. So if you look at the next part of this problem that we're going to do, we've already found all the eigenvalues and eigenfunctions. We're going to do an orthogonal expansion, so you can think of this as a Fourier sine or cosine expansion, but it's using these eigenfunctions that we've never used before. So what the theorem says is that I can take the function x, right, and I can look at this inner product, and we're going to look at this real quick. This inner product, this weighted inner product, we're on the interval from 0 to 1, so by definition, this would be the integral from 0 to 1 of yn would be e to the minus x over 2 sine n pi x. Ym would be e to the minus x over 2 sine m pi x. And then you have to multiply by the weight, and if we go back up, the weight function here was e to the x. So I have to multiply this by e to the x. And I want you to take a look at what happens here. It's actually kind of crazy. This is yn. This is another member of that set ym. This is our weight function. And if you look, the weight function is the perfect function to cancel the e to the minus x over 2 that we had here and here, so that this ends up being an orthogonality relationship that we recognize. Look, e to the minus x over 2 times e to the minus x over 2 is e to the minus x, but then e to the minus x times e to the x is 1. So this just ends up being this, which we know from our previous dealings with Fourier series, this thing is 1 precisely when n equals m, and it is 0 when n does not equal m. So this is indeed orthogonality with respect to the weight e to the x. And these functions have that orthogonality property. And because of that, for any function that resides in the L2 space on 0 to 1, we can expand f of x as the following. And for this example, we were asked to expand the function x, so I'll just show it to you for the function x. You can expand x as a sum and goes from 1 to, I'm not going to do infinity, I'm going to call it capital N, of Cn Yn, which is, for our problem, the Yn are e to the minus x over 2 sine n pi x. Those are my eigenfunctions here. And you were told that Cn is the function f of x, which is x, yn, weighted inner product, divided by yn inner product. So this is like the norm squared of the weighted eigenfunctions. And so this would be the integral from 0 to 1 of x e to the minus x over 2 sine n pi x times e to the x, don't forget the weights, do not forget the weight functions, over the integral from 0 to 1 of sine n pi, whoops, almost made a mistake, it's the weighted one. It's e to the minus x over 2 sine n pi x squared e to the x dx. Notice down here on the bottom, you don't square the weight function. It's just the yn is squared here. And if you notice, this actually reduces rather nice on the top part here. This e to the x and e to the minus x over 2 is x e to the x over 2 sine n pi x. And then if you look at it in the denominator, you get e to the minus x over 2 squared, which is e to the minus x, times the e to the x that's there. Those cancel. So you end up with our normal sine squared in the bottom, which we know is half of the interval length, which is 1/2. So you're dividing by 1/2, you end up multiplying by 2, and this looks a lot like those Fourier sine series that we've been working with earlier, but these are your coefficient formula. So this is the coefficient formula for this orthogonal expansion in terms of these new eigenfunctions. And we can evaluate the error of this, right? We can go into Maple, which we're going to do here in a second, and look at the integral from 0 to 1 of the function x minus its orthogonal expansion, which I'll keep calling, even though this isn't a Fourier series, I think we've gotten used to this, I'll keep calling this f sub n of x. So this is f sub n of x. This is that orthogonal representation. So we're going to look at this thing squared. It's the absolute value times the weight function, like so. So we can look at that in Maple, which we're about to do. I'm going to show you this example is available to you to look at in Maple. So it is right here. The title of the Maple file is Weighted Orthogonal Expansions. So here's the SLP that we just looked at. My function is x, my weight is e to the x. We obtained these eigenvalue problems, or eigenfunctions for this eigenvalue problem. I simply coded the coefficients, formed the partial sum of the representation, and if you look, it all turned out looking really good. So this is our try at representing the function f of x equal to x on the interval from 0 to 1 in terms of these new eigenvalue or eigenfunctions. And here we have the L2 error. So this is the weighted L2 error because I'm multiplying by e to the x. And the problem on this asked to find how many terms of the sum you need to ensure that the error is less than 0.1. So it actually gets a little bit tricky if you try to solve this function for k such that this function is equal to 0.1. So if you can do that, great, but it's okay to start listing out some values to figure out what the error is at larger and larger. And we didn't get under 0.1 until we hit 55. So you need 55 terms of this series to get an L2 weighted error under 0.1 for the entire interval from 0 to 1. So we're definitely going to be using this coming up really, really soon. This is an important result in this course and moving forward into the problems that we're going to look at on Friday, Monday, and Wednesday of next week. All right, so if we head back to the notes at this point, what I need to do now that we've done an example with this and seen what's going on is I need to go back and prove a couple of results here for the regular SLP theorem. We're going to start with proving that the eigenvalues are real. In order to do that, though, I need to prove that the SLP operator is symmetric with respect to the weighted inner product. Couple of different ways to view this. The inner product USV SU, V, W. This is S applied to a function V, and then you have U, and then this is in other words, this is a solution. This is a eigenfunction, right? So SV is an eigenfunction. This is the eigenfunction for U. U is just a function, and then SU is its eigenfunction form, if you will. I need to show that these two things are equal to each other. But if you look at what I have just above here, we can prove, if you take the forms of what these things are, the SLP forms, we can prove that USV minus VSU is given to us by this. And if you integrate both sides of this result, you obtain the following, which is starting to look an awful lot like integration by parts. In fact, it's very much related to integration by parts. This is something called Green's identity, which states that the difference, it's called the symmetric difference, by the way, the symmetric difference of this inner product is equal to this value over here. And what we're trying to prove is if you have a regular SLP that satisfies symmetric boundary conditions, we're trying to prove that this term right here vanishes. So here's what we're going to do. To conclude that USV equals SUVW, we need to show that the right-hand side of, and I'll label this equation with a star here, that the right-hand side of star is 0. Well, so what we do at this point is we say, okay, if we have symmetric boundary conditions, then they are of the form, if you go back to the very first note in this video, the symmetric boundary conditions are of the form alpha 1 U of A plus alpha 2 U prime of A equals 0. Beta 1 U of B plus beta 2 U prime of B. So whatever the function U and V are, they have to satisfy these boundary conditions, which means I have this relationship on U, and I have a similar relationship on V. Because they're both solutions, they're both assumed to be solutions to the same SLP problem. So you've got alpha 1 V of A plus alpha 2 V prime of A equals 0. And beta 1 V of B plus beta 2 V prime of B equal to 0. So we know that the symmetric boundary conditions are of this form. They imply this relationship between U and V. And if you look real quickly, I can immediately write down. So I'm going to focus on showing that this vanishes at the top input, which is UB, VB, U at B, V prime at B minus U prime at B, V of B. I'm going to focus on showing that that term vanishes at B. And then there's going to be a similar result at A, but you're just going to do the exact same thing I show you here to show that it vanishes at A. So if we know this, then we can automatically solve here for U of B. I'm going to take this bottom equation here, and this means that U of B is minus beta 2 over beta 1 U prime at B. And we also know that V of B is the same thing. It's minus beta 2 over beta 1 V prime of B. But I can take those results and say, okay, let's look at that right-hand side. So U V prime minus U prime V. So U V prime minus U prime V. And what you notice is if you plug these results in, you will get minus beta 2 over beta 1 U prime plus beta 2 over beta 1 U prime of B, V of B. And lastly, you can reverse these things right here to solve for u prime. So you could get that u prime is minus beta 1 over beta 2 u of b. And you could get that v prime of b is minus beta 1 over beta 2 v of b. And you can see where I'm going to use that. I'm going to replace u prime of b with this. But notice you get minus beta 1 over beta 2 minus beta 1 over beta 2. Those cancel. And then you just have u of b, v of b right there. And then here, if you replace u prime of b there, right, then, sorry, that derivative there should be there. But similarly, if you replace u prime here, you get minus beta 1 over beta 2. Those cancel out. And what you end up having is, because it's a negative, when you replace it here, it's minus u of b, v of b, which turns out to be 0. So the conclusion then is, at least at b, this right-hand side disappears. And you can do a similar argument to show that the right-hand side of this equation disappears at a, which implies that the symmetric difference of these orthogonal inner products is 0, which says that they have to be equal to each other. And if they're equal to each other, then this property is known as symmetry. In other words, you can look at the SLP acting on either part of your inner product interchangeably, and it still gives the same inner product result. So what we've proved is that SUV is USV with respect to the weight W. And that's going to be important to prove what we want to prove. We're going to prove 1 here together, and then I have a video, an additional video that has a proof of 2 in it. So we're going to prove that the eigenvalues of a regular SLP are a real increasing infinite sequence. I'm not going to prove the increasing and infinite sequence part. You can check that out in your book, but I do think it's important that I work with you to prove that anytime you find eigenvalues of a regular SLP, those eigenvalues will always be real. You'll never end up with complex eigenvalues in this course for solving these regular SLP problems. All right, so the proof here is actually pretty straightforward now that we've proven symmetry. What we're going to do is we're going to suppose that lambda equals alpha plus beta I is the eigenvalue of a regular SLP with associated eigenfunction I think I just used y. Yeah, y of x equal u of x plus I v of x. So we're assuming the possibility, we're supposing the possibility that the eigenvalue is complex. Now, if I can show that beta has to be 0, then that'll imply that it's real. So keep that in our back pocket. But we're going to suppose that the eigenvalue is complex and that it has a complex valued, complex valued function of a real variable. Y of x equal u of x plus I v of x is its associated eigenfunction. Then we automatically know, because complex conjugate roots occur in pairs, we automatically know that lambda bar, which is the conjugate, is an eigenvalue. And it has associated eigenfunction. Given by its conjugate, which is the function u of x minus I v of x. Now, what's interesting here is if you look at what this means, if they're eigenvalue, eigenfunction, then that tells me that sy equal minus lambda y, that's what it means to solve an eigenvalue problem. It solves the sy plus lambda y equal to 0 problem, the regular SLP problem we were looking at earlier. And so too must the conjugates solve those problems. So we know that this relationship is true for our SLP, sy plus lambda y equal to 0. So I want us to consider that symmetric difference that we just looked at for these eigenfunctions. So we're going to look at this minus this. So we know we have solutions to the differential equation in terms of the eigenfunctions y and y bar. So the previous result holds. We know that this symmetric difference is 0 because we know that the SLP operator is symmetric, so we know that these two things are equal to each other. However, if we revert this to the integral definition of what these are, right? This is y times sy y bar times the weight function w of x. So this would be y sy bar minus sy y bar times w of x dx. That would be the definition of the difference of these two inner products. Now, I think you can see where this is heading. What if we replace sy bar with minus lambda bar y bar? And replace sy with minus lambda y. Then what you can immediately see is we have y bar in both terms, and you have lambda plus lambda minus lambda bar, which can be factored out because they're just constants. So it reduces to this. Now, here's the thing. We know that both of these are eigenfunctions to the same eigenvalue problem. So the only way that this term is 0 is if both of these are 0, which is crazy. We don't want this to be 0, which means that lambda must equal lambda bar. But if lambda equals lambda bar, what does that mean? If a complex number is equal to its conjugate, then that means that alpha plus beta I has to be equal to alpha minus beta I. And the only way that's true is what? The only way that's true is if beta is 0. So the conclusion is that the eigenvalue that we were looking at, that we assumed we had, must be real. So you will not have any complex eigenvalues when working on these problems. Now, the other thing that I want to prove, but this video is already getting pretty long, is that the sequence of eigenfunctions are orthogonal. The sequence of eigenfunctions we get from regular SLPs are orthogonal with respect to that weight function w of x. I do want you to see and work through the proof of this, but I want you to see the video linked on the SLP page in Canvas. So there's a lot of terminology here. There are a lot of formulas that we showed in this video. Keep in mind that this is an attempt to generalize what we've been doing in the course so far so that we can open up harder, more interesting looking PDEs in the coming days. All right, thank you for watching. Don't forget you do have a quiz due this weekend on Friday and homework due on Sunday. And if you have any questions, let me know. I hope all of you are doing well out there, and I will talk to you later.